Today, we're digging into a question that sounds simple, but it uncovers this profound, mind-bending new idea about the universe. And that question is, why do the forces that run everything seem to have an end? It turns out there might be a single universal rule that governs all of them. So just think about it for a second. The sun's gravity obviously holds the Earth in orbit. It even reaches all the way out to Pluto. But what about, say, a spaceship that's halfway to the next star? Is the sun still pulling on it? And does that pull ever actually stop? It feels like a simple question, but it opens up this massive puzzle in physics. Okay, so let's dive right in. As far as we know, the entire universe is run by just four fundamental forces. You can think of them as the main characters in our story today. And the really weird thing is, they all behave in dramatically different ways, especially when you look at how far they can reach. I mean, just look at the sheer scale of this difference. It's kind of nuts. The strong nuclear force, which is the glue that holds atoms together, basically vanishes over a distance that's almost too small to even comprehend. The weak force, even shorter. But then you have electromagnetism and gravity, which theoretically are supposed to go on forever. So how? How can one universe have rules that operate on such wildly, completely different scales? This is what physicists call the cosmic range problem. Now, for centuries, physics has had a kind of standard answer for this. The problem is, while it's mathematically, well, beautiful, it just feels physically incomplete. It doesn't seem like the whole story. The textbook answer you probably learned is the inverse square law. And it really is a beautiful piece of math. It basically says that a force like gravity gets weaker the farther away you get, specifically by the square of the distance. So, if you double the distance, the force is only 1/4 as strong. It just gets weaker and weaker and weaker, but here's the catch. Mathematically, it never actually hits zero. It just goes on forever. And that's the problem, right? An infinitely weak force acting over an infinite distance, that doesn't really help us understand the effective ranges we actually see and measure in the real world. I mean, at some point, an influence has to become so weak that it's just irrelevant, doesn't it? The whole idea of infinity just feels like it's missing something. It's not a complete physical answer. And look, physicists know this. In practice, they use all sorts of cutoffs to define where a force's effective range ends, whether we're talking about a planet's gravity or what's happening inside an atomic nucleus. But these have always been seen as, local workarounds or convenient approximations. They're not seen as a fundamental rule of the forces themselves. And this is where we get this radical shift in perspective. What if we've been looking at the whole problem from the wrong angle? What if the secret isn't in the force itself, but in the actual space it's traveling through? So here's the crucial new idea. Let's stop focusing on how a force gets weaker. Instead, let's focus on how space itself might have a limited ability to even respond to that force. The force might be infinite, sure, but maybe the response of space is not. Here's a really simple way to picture it. Imagine dropping some dye into a swimming pool. Right where you dropped it, the color is vibrant and strong. But if you go all the way to the other side of the pool, even if a few dye molecules made it over there, they're so spread out that the water's color is totally unchanged. The influence is technically there, yeah, but it's become structurally irrelevant. The water has, for all intents and purposes, stopped responding. This whole concept is called phase saturation. The theory suggests that space isn't just a perfectly smooth, empty canvas. It has a kind of fundamental texture. And as a force's influence travels through this texture, it's like a signal that's accumulating noise or static. Eventually, that signal gets so garbled that space just can't process it coherently anymore. Its ability to respond gets maxed out. It becomes saturated, and that's where the influence effectively ends. This brings us to the absolute core of this idea, because if this phase saturation thing is real, it should follow some kind of consistent rule. And it does. An astonishingly simple and universal principle that seems to connect all four forces. So here it is, the big question. From the tiniest subatomic quarks to the vastness of our solar system, we're talking a scale that spans more than 30 powers of 10. What single hidden rule could possibly be defining the effective range of everything? The answer, believe it or not, is this strange little number, roughly 3.2. Now, this isn't a physical constant like the speed of light. It's what's called a structural number. It seems to just emerge from the very geometry of space. And according to this new theory, it's the key to everything. So here's how the rule works. It's actually pretty simple. First, a force's influence travels outward in these discrete steps, which we can call structural shells. Second, the response of space just stops after the influence crosses about 3.2 of these shells, and that number is always the same. It's universal. And third, the only thing that's different between all the forces is the physical size of their shells. That's it. This is the whole idea in a nutshell. The strong nuclear force has these incredibly tiny shells, so it hits that 3.2 shell limit almost instantly. Electromagnetism has larger, atomic-sized shells, which gives it a much longer reach. And gravity? Well, its shells are just enormous, so it takes an astronomical distance to cross 3.2 of them. It's the exact same rule, just playing out on completely different scales. How elegant is that? Now, claiming there's a universal rule for everything is a pretty bold claim. So what's the evidence? This is where the theory goes from just being a cool idea to a really compelling new framework for how we look at the universe. All right, here's the crucial piece of evidence. The researchers took the known effective ranges for all four forces. They calibrated their 3.2 shell model using only one of them, the electromagnetic force. Then they turned around and used that model to predict the ranges for the other three. And the result? Well, as you can see in that final column, they all produced a ratio of almost exactly 1, a perfect match, across more than 30 orders of magnitude. I mean, come on, that's not a coincidence. That has to be pointing to some deep unifying principle at work. So this new structural view really represents a profound shift in thinking. The old view sees these infinite forces, each with its own separate, complicated rules. This new view suggests no, all forces have a finite effective range, not because the force itself dies, but because space stops responding. And crucially, they all seem to obey one single universal rule. This quote from the paper just encapsulates the main takeaway perfectly. The mathematical description of a force might stretch on to infinity, but the physical, structural response of the universe itself does not. It has a clear and definable end. And this leaves us with a final, really powerful thought. By just reframing our original question, we find a completely new answer. It turns out the question isn't, how far does a force go, but at what scale does space stop responding? And with that one simple shift, all the chaos and confusion of our universe's forces suddenly snaps into a single unified picture.